Все? Ну, спасибо. Вот, so, okay, on previous class we have started discussing the linearization, but today I want to first talk about the Rosen-Licht theorem, which gives you the rational quotient. So far we know that for X affine variety, a G reductive, linearly reductive, we have the quotient X modulo G, a categorical quotient. With good properties, yeah. So today I want to discuss the rational quotient. So far we have discussed that this quotient parameterizes closed orbits in affine variety. So it parameterized as closed orbits in X. But of course, sometimes it is important and convenient to discuss generic orbits, on the open subset. So today we shall discuss rational quotients, and next time I think we shall start today. We will discuss the so-called Mumford quotient that was the general construction for projective variety that allows you to construct quotients. So it won't be the categorical quotient in the sense that it is categorical for affine varieties, but it will be a good substitute. So today we shall start with rational quotient. So in order to start constructing quotients, of course what we have noticed that the invariants are usually, so the invariants, so if you have the quotient, the map to the quotient should be given in terms of subalgebra of invariants. So the idea is the following. So, and what can also happen? So notice that in the natural example of projective space, so if you look at the functions on, so if you look at the functions on affine variety, yeah, so of A2 with the action, so xy maps to tx and ty, then you see that that here there are no invariants. So invariants of this algebra are only constants. And the reason, of course, that the orbits come together and have the common orbit, so the smallest common closed orbit, and this tells you that you cannot, so if you want to have the rational functions, it should have the same value at the orbit as in the closure, and there is a common point for all orbits in the closure, so you have the invariants that are constant. So you see that if you exclude this point, so excluding this point gives you, of course, it prevents, I mean, you will have different orbits, and they have nothing in common, but however, so you can think of the following. So you can, for example, take out the line, so take out some line out of this picture, for example, y equal to 0. And now you can consider the rational function. So rational function invariant. So of course, if you pass to this open subset, it is equivalent. So if you take this U, so K of U will be the localization with respect to Y, yeah? So with the powers of Y. So these elements are just fractions of xy divided by yk. And if you look at, so you can consider rational invariants, so or invariants on this open subset. And this invariance on this open subset, it looks like, so for example, you can think of this as a polynomial written in x divided by y. Yeah, so just f of x divided by y. So this is a polynomial in one variable, so k of t, where t is just the fraction x divided by y. Yes, so you see that multiplication by t does nothing here, and this is a natural function that have pole along this line. And on this line, of course, if you look at this function, it is just a slope of the line. And if you think, so of course it distinguishes the lines on this open subset. So just k of t distinguishes orbit, distinguish the values of these functions, distinguish orbits on the open subset, on U. And the idea is just to do the following. So in order to construct quotient, and what does it mean? I mean, if you restrict something to the open subset, this means that you are passing to the localization. And if you think of the largest thing where you should search for invariance, it is of course fraction field. So the idea, find the functions, invariant functions, rational functions, so the elements of the fraction field of the regular functions. I mean, if x is affine, yeah, so just so when x is affine. But at anyway, so there exists these functions, and for rational functions, you can say what is invariant function. So you may think of the following algebra. And so the idea of find the functions that distinguishes orbits. Yes, so that distinguish orbits on some open subset of x. Yeah? Some u of x. So meaning that there will be the function that so that has different values on different orbits. So let me formulate it. So theorem of Rosenlicht. So if so suppose just g acts on x, notice that g is only supposed to be a affine group, so possibly not reductive. So x is algebraic variety, but possibly not affine. So then then there exists a collection of functions the rational G-invariant functions and the open subset and the G-invariant open subset U. Open subset U such that just for any x and y, just gx is the orbit is equal to gy if and only if the values of these functions on these points are the same. So this is just as for the points, this can be viewed as the points over K, but of course, so the field is not important here. So over K, some field, possibly not algebraically closed. So this is, notice that invariants, if you restrict to some open subset, invariants can behave rather tricky. First of all, it is, so there are some remarks about this. Remark just in this theorem. So U is not supposed to be, I mean it is, so when you are working with algebraic geometry, so it is natural to restrict everything. I mean if you have local situation, so it is natural to restrict it to the open affine subset. So, and just apply commutative algebra. So here it is, there is a slight problem. It is, if you are speaking, I mean, if you wish to speak about the orbits and the actions, so the orbit, of course, should be contained entirely in the open subset, and at least the open subsets that you should consider should be invariant. I mean, if you want to formulate the theorems like this. But the problem is that it can happen that you cannot cover by your variety by G-invariant affine charts. So it can happen. It can happen that variety cannot be covered by G-invariant affine charts. So this is so here you have easy example. So example is of course G mod B. Yeah? So this is G mod B. It is projective and homogeneous. Yeah? So if you are covered, it should be coincide. It is the only orbit, so it should coincide with its own chart. So and it is projective. Yeah? So just since it is complete, homogeneous and complete. It is not covered. But there are good news, but under additional assumption. So one can. So this is. What we know about this? So we know the theorem about homogeneous spaces. Yes. So the homogeneous spaces can be realized as the subsets of projective variety. So maybe it is. So the question is that. So we cannot cover them by affine charts, but what if we can cover something by projective varieties which where action comes from the action on the vector space. So the action is linear. And this is the so-called Sumihiro theorem. Да. Где? А, вот здесь? Ну да, давайте тут как бы... Ну а если x приводимо, то вы по делителям нуля, как бы, да, ну, по неделителям, ну, в смысле, локализуете по неделителям нуля. Ну, да, как бы. То есть применяйте конструкцию локализации, но не в делителям. Но, вообще говоря, как бы тут достаточно, в общем, более-менее для неприводимого доказать теорему. Ну, тут сразу же понятно вот что, то есть, ну, как бы, если у вас есть несколько компонент, да, то вы, даже если они зацеплены между собой, ну, вот во время действия, то все равно вы можете, ну, их общие пересечения, ну, как бы объединение вот их пересечений будет инвариантным подмножеством. То есть, ну, как бы, поэтому то, где они пересекаются, будет инвариантным подмножеством, это можно выкинуть, поэтому можно уже сразу считать, что у вас есть дисъюнктное объединение компонента, это уже произведение полей. Поэтому как бы... То есть, ну вот единственная сложность в том, что вы как бы говорили, да, ну что как бы что компоненты могли бы пересекаться, но вы всегда можете перейти тут к инвариантному подмножеству. Хорошо? Ну, в смысле произведения полей на каждой компоненте. Ну, функция на компонентах — это произведение функций на каждой компоненте. Рациональная функция на объединение компонент — это произведение рациональных функций на каждой из компонентов. Ну, как колец. Да? Это кольцо, но не поле. Нет, я же не говорю, что это поле инвариантных, ну, функций. То есть это, конечно, будет не полем инвариантных функций, но это будет произведение полей. Ну, в смысле, что k от x будет произведением полей, а g — это инвариантная функция. Ну да, если x не приводимо, то не обязательно. Ну, да. So I wanted to state some Hero theorem. So this is the question how we can just cover our variety. So suppose x is normal. So the only important technical assumption is that so you cannot formulate this theorem without this technical assumption. It is just not true. But if you assume that x is normal, then there exists UI G invariant subsets such that x is covered by this invariant subsets, and so for each subset there exists G equivalent embedding so UI inside P of EI, where VI is G module, is a representation of G, So the action on Vi is just linear, and so Ui is realized as quasi-projective variety. So quasi-projective. So meaning that it is open in its closure in P of V. Yeah, so just intersection of open and closed subsets. And this, of course, explains that GB is just a chart for itself in this sense. Yeah. So, but of course, there is a benefit. Yeah. So, if you are thinking about P of V, of course, if you can think of the cone, yeah. So you can take the cone. So, if you want to study UI and you have the linear action, you can take a fine cone in Vi, so such that if you you look at Ui without 0, it maps precisely to Ui when you are taking projectivization. So this diagram is commutative. There is additional K star action. And of course, what is good about this thing, so here you have additional G times K star action, where K star act by homotheties. And if you want to think of quotients, so quotients here are just GK star quotients here. But of course, it can happen that they have somehow, I mean, you should be very quotient when you are just factorizing by this group here, because if you add 0 and if you exclude 0, you can get different answers. So let me discuss now Rosenlicht theorem, proof of Rosenlicht theorem. So the idea is of the proof is to reduce this to understand. First, we shall understand how big should be this open invariant open subspace, and then we shall discuss this Fi's as the generators. So but of course we shall be picking this open subset gradually, because these are the elements of the fraction ring, and so they have denominators. So in the end of the day, we should exclude also poles of these functions from our open subset. But it is not restricting. They are all, if you have G invariant function, the poles are G invariant. Yeah. So let us start. So so notice that there exists an open subset. So we have discussed the theorem on semi-continuity of dimensions of orbits. So there exists an open subset of X where orbits have the same dimension. Yeah, so this is possible due to our semi-continuity principle, so that or Chevalier theorem on the fibers applied in the special form. So this. So this we can pass to the open subset. So then I want to consider graph of the action. So graph of the action. So notice that so here you have so here we have our action map ρ. And here we can map so we can take the map from gx to x times x. So by mapping gx to gx times x, and as the morphism, it is just rho times identity. What is good about this thing? So and this is phi, and the image of phi is called graph of the action. So what is good about this action? That because so if you look at this gamma inside x times x, you can pick up projection. It is not important which projection. So, for example, P2. And if just if you take the pre-image of x intersection with gamma, it is just what? It is just those points of gx that so for x you should find the g such that gx so these points are equal. So this pre-image is just isomorphic to the corresponding orbit of gx. Yeah? So so this is this is about the graph. But now I want I want to use this graph and notice that so this somehow plays roles of the quotient. So the space x itself, it somehow parameterizes orbits in x, but it is so the information is superfluous. There is it considers several orbits several times. Yes, so the orbits of different points can coincide, of course. So, but what is good about this map? The fibers of this map are precisely the orbits. So this will be important for us. So, but problem that this graph can be not a priori closed. So I want to describe gamma as the set of zeros in so at least locally. So a problem that gamma is not closed. So if and how to make it closed? So just take the closure. And but of course it can happen that I mean, if you look at the corresponding fibers of the projection, this means that to the orbit you should add some more orbits. Yeah? But what can be said about the just if gamma? So I claim that in my situation, gamma can be assumed to be closed by the following observation. So, I mean, if you just under the assumption of the theorem, gamma is not closed, but we can reduce it to the closed case. So, how can you do it? So, take the complement. Yeah, so, y to be the complement of the closure. And then I want to do the following. So take P2 of y, and I claim, so it is the subset in X. So I claim that that P2 of y is not dense. In X. So you can do the following. So you can do if we prove this claim, then we can take the closure of P2 of y in x. It is not equal to x, and throw this away. So just take x0 to be x without P2 of y. And of course, if you think about now the graph of, so this is, yeah, so of course this is G-invariant subset. So this is also G-invariant. And x0, so you can pass to the intercept. So the graph of x0 is just the intersection of the graph with x0 times x0. And this thing is already closed. Since if the non-closed part, the part in the closure, y in x0, it is empty because the P2, the second projection is 0 here. So just is this empty set, since projection P2 of y is, so it is doesn't intersect x0. And now the proof of the claim. So in order to do this, it is sufficient to estimate the dimension of P2 of y. So just we can calculate. So we can estimate dimension of P2 of y. And this is, of course, as follows. So the dimension of P2 of y is just it is less or equal than dimension of the variety you are projecting minus the dimension of the fibers. Yes, so you have dimension of generic fiber. Yes, so you can just so actually there is actually dimension of P2 of y is dimension of y minus dimension of generic fiber in y. Yeah, but this is gamma is the proper subset of y is the proper subset of gamma. Then this is less or equal than dimension of gamma minus 1. Yeah, so it is at least, so it should be smaller since gamma is open and gamma overline. So the dimension of y should be strictly smaller than dimension of gamma, and which is also the dimension of the closure, and minus the dimension of generic fiber. Yeah? So this tells you, so notice what is dimension of gamma. Yeah? So let us calculate. So under our assumption, so what is the dimension of gamma? Yeah? So we have in X we have all orbits of the same dimension. Yeah. So, and gamma, of course, gamma projects surjectively to x. Yeah. So P2 of gamma is just the whole x, because you can take any point and look at the corresponding orbit. So dimension of gamma is just, and all fibers has the same dimension. So it is dimension of the base plus a dimension of fiber, so generic fiber. But these fibers has the same dimension. So a dimension of x plus dimension of orbit. So this set, so this is fixed constant. Yeah, so fixed constant. And in the same time, so the fiber of so this fiber in y. Yeah, so if you take intersection of y and P2 of P2 inverse of z. Yeah, so this for some z inside the image. Yeah, so maybe I should have written it like P2 of some y and P2 inverse. Yeah, so for y inside y. So this subset is G invariant, of course. So this is G invariant. Yeah, because you are not, so you are taking the point in the second projection, so and the action on this set is just, you are looking at the action only that comes from the action on the second factor. So this is G invariant, and then it consists of orbits. Yeah, so that it consists of orbits. So its dimension is at least bigger than dimension of orbit. Yeah, so that. So this means dimension of this fiber is bigger than dimension of orbit, but this is fixed constant. Yes, so this is just let us put it to some constant m. So this is m. And so this means that in this inequality, so dimension of P2 of y, it is bigger or equal than dimension of gamma minus 1 plus dimension of generic fiber. So this is dimension of x plus less or equal, yeah. So dimension of so plus m. This is just dimension of gamma minus 1. And minus, so here you are, so here you have the estimate that the generic fiber is bigger than m. So this you have, again, this equality is better if you put dimension of gy here, so which is equal to m. So this tells you that this number is just dimension of x minus 1. Okay. I have changed the dimension of generic fiber by this estimate, and this is just dimension of gamma. So you see that the dimension of the subset is just, this is a smaller subset. Okay? So this means that P2 of y is a proper subset. It's more just not equal to x. So we reduce this to this case. now gamma becomes closed subset in x times x. And now I want to make the following trick. So just in fact, we're thinking of if you have already distinct orbits, yes, so if they are of the same dimension, then we can check not our property, but somehow a weaker property. So in order to check that gx is, we have to check that for the orbits, so we have to check that the orbits are not equal, but you may think of checking that the idea is that you can look at so what we really want to check, so we can pass to the open subset. So we can pass to U inside X or some open subset, possibly not G invariant, and to distinguish, notice that just the set of rational functions on U is still the same as the set of rational functions on X. You do not have the action of G, but still, so here you have the subset of rational functions, G invariant rational functions. So when you pass to the open subset, you still have invariant functions. However, you do not have the action already on U. So the orbits U can be smaller. You can intersect the orbits properly. But our problem is just to distinguish the intersections of orbits with some open subset. So just aim to distinguish intersections of orbits to some open subset. So just notice that gamma now becomes, so now gamma is a closed subset. So you may think of it as the subset in you may think of it as the subset in U times U, and if U is affine, so gamma is defined as by some ideal. Yeah, so just U is affine, but possibly not G invariant. But gamma is defined by some ideal here. So gamma is defined and this also you may think of so this is ideal in K of U. Turns K of U. Or you may think that gamma is defined by the sheaf of ideal. yeah, in the corresponding subset. And also note that you can pass to also. This you may think of this algebra as the algebra of k of u times k. And here gamma still, so this means that up to this means that here I do not specify the open chart I'm considering here, but if notice that gamma is very specific, if it is, so note that by construction, so gamma projects dominantly to just by P1 and P2 to U and to any x. So so gamma U, so intersection of gamma. So gamma U is just intersection of gamma with U times U, of course. And so gamma projects dominantly to both by P1 to Pu. So this means that if you take any intersection of, so if you take gamma and take intersection of with some closed subset, some open subset, then this set is not empty. Yes, so for V times U is not empty. So this tells you the following. So this tells you that you can just pass to so this means that if you take the ideal I gamma, so I gamma, and extend it to ideal of k of u times k of x, k of u. This will be, so which is just the k of x times k of u. This will be just, it will be, so extending means that I simply take to be the algebra B and to consider, so by extension of ideal, I mean that I just consider the ideal generated by this elements of the set in the algebra of B. So this is just the products of I of gamma with elements B, and this means so that this ideal defined non-empty closed subset really means that I of gamma B is not equal to B. Yeah? So it is not the whole set. And this just this ideal B is just what? V is just some, so for some open subset V inside X, open affine subset of X. So I mean that the gamma is so big that if you even intersect gamma with the products of two open subsets, then it will be a non-empty set. This means that gamma generates non-trivial ideal on this set for any V, and this also means that you can just, since this holds for any V, so for any collection of elements, your ideal still cannot generate the ideal in. So since this is a non-empty set, the ideal generated by, so when you are passing to this from, so the ideal of this intersection, yes, so that corresponds to this intersection is just taking ideal of gamma and multiplying it by the corresponding algebra, k of v tensor u, k of u. But since this is not equal to the whole k of v tensor k of u, when you pass to the limit, so to get the fraction field, so you still have that so this inequality for your ideal. And when you are considering it in this fraction field. But what is the benefit? So let us understand how to how to write down this ideal. So here you have this yeah. So let me have a slight look here. So this, yeah, so now we are considering the finitely generated, so since we are considering varieties, so you have finitely generated algebra, yeah? And this finitely generated algebra is just, yeah, so, so here there should be some important lemma that, yeah, so this is fine, so k of x times k of u is finitely generated algebra, so finitely generated algebra. So the ideal, so this ideal I of gamma times b is also finitely generated. And also you notice that, so here you have, so on this field, so this ideal is, I mean, if you look at gamma, so it is invariant if you apply g action on the left factor. Yeah, so here you have, so here you have action of g, so action of g on the first factor. And when you're thinking about this action of g on the first factor, gamma is invariant with respect to this action. Yeah, so of course, yeah, so gamma is of the form of these elements, and you just can multiply g by any element of g. It is still there, so you can write down like this. Yes, so it is still the element of this form. And this tells you, yes, so that gamma is invariant, and I shall need the following lemma. So just important lemma about. Yeah, so gamma is finitely generated, so this is finitely generated ideal. And now I want to speak about generators. So here you have the following situation. So here you have now lemma. So yeah, so notice that everything. So here you have so this kfx is also. So this is so kfx contains natural. So it has an action of G, and contains also it contains the set of invariants. Yes, so the k of x G, so it contains the set of invariants, the field of invariants. Then I want to consider the following lemma. So take k of t and k and k field extension, so some field extension, and consider the tensor product of your. So suppose you have the vector space. So you have the vector space V, which is a tensor product written as the tensor product of k over k of some other vector space W with the trivial action G action. And consider here, consider the action, so consider the G action on V via the action of via the action on just on this coefficients. Yes, so via the action on coefficients k. Yes, so coefficients. So you have coefficients xi, wi, so it maps to g of xi, wi. And suppose you have assume you have the following. So assume you have yeah, so assume you have just U inside V is a G invariant subspace. Then I claim that yeah, so then I claim that then yeah, so then there exists basis in U that is is that consists of G fixed vectors. So G fixed vectors and this notice that that G fixed vectors are not only the vectors written in the form Wi. I mean, so since you're thinking of Wi as basis of W, so that you are writing the vector in terms of xi times Wi. Yes, so this means that G fixed vectors will be of the form. So fixed vectors are of the form just yi wi, where yi belongs to the G fixed vectors of K. Yeah, so because Wi basis, so if you apply if you apply G to such combinations, so it is equal to yi W I if and only if yi equal to ig. Yeah, so since W is the basis. Yeah, so W is the basis. Okay. Хорошо? Понятно? What? No, G can act non-trivially on U. Yeah, but of course the elements of U are written of the form sum just of some lambda J times the basic vector. But this basic vector is just, well, it is written as Wi, and so in this basic vector, these are both G invariant elements, but lambda, it can act non-trivially on this coefficient. Yes, so that means that the elements of U are not fixed. Yes, so the linear combinations of such vectors times arbitrary linear combinations from the field K are not fixed. But if the space is invariant, then you see that you will have here, you will have the collection of invariant elements times some coefficients from the field, and the action is mainly just is the action that comes from this part. So this is a dilemma that we shall easily prove, and it will give you actually what I want to have. Yeah, so notice that so here just proof of dilemma. Induction. So here notice that so notice the following. So notice that of course what is the problem in this lemma that we really see? It is hard to make induction because I do not claim that U and V are finite, U and W are finite dimensional. Yeah. So да.
Вот если у нас базисные векторы в U, они же фиксированы, нормализированы.
Да.
То значит, линейные комбинации тоже.
Нет, Потому что если вы умножаете басенный вектор на коэффициент неинвариантный, то этот вектор не остается неподвижным. Вот как бы в этом-то и как бы основная идея, что почему эта лемма работает. То есть это как бы у вас вся неинвариантность действия приходит из коэффициентов поля, да, то есть вот из элементов отсюда. Хорошо? Да, К это поле, Ж действует. Ж это подгруппа автоморфизмов К над К, но К не является, ну это как бы одна, ну это более-менее теорема из теории Галуа, но как бы, ой, извините, я сейчас отвечу. Давайте перерыв сделаем как раз. Сейчас. Алло. Сейчас. Алло. Yeah, it is more or less theorem on the Galois theory. However, in the Galois theory, you see that K is in the Galois theory, you see that K is just equal to the set of invariants. Here, of course, so here we only assume that K is a subset of the set of invariants, and it is some kind of generalization of this theory. So let us do the break. So after the break, I shall prove the lemma, and we shall derive the theorem.
Мне передали, что можно до 19 числа, к 19 числу нужно сразу прислать, и там первый листок.
Да.